In order to guarantee full understanding of this course, you should have completed previous universal molding modules. MU1 Introduction, MU2 Fundamentals, MU3 Molding with Graphs, MU4 Material Morphology, MU5 Press Calculations, MU6 Injection Unit Calculations, MU7 Cooling Calculations. Remember that your objective should be to identify the requirements of your process and attend those needs with well-thought-out solutions. Universal molding is a discipline that promotes a structure of organized events. Remember that you are working with expensive equipment. Do not rush your work and follow all safety regulations established by your company and your government's agencies. You can never be too careful. In this module, we will discuss plastic melt flow, shear stress, viscosity, and shear rate, machine rheology, rheology by power, approximated rheology, equation to predict injection time, plastic melt flow. The movement of material through a mold's cavities or runners is better understood if we visualize the flow as short, fine strings suspended in a melt. These strings are polymer chains that float freely, and their orientation depends upon the direction of the flow. These strings are molecules that conform to a specific orientation, which is determined by both flow and cooling time once the material solidifies in the mold. The following illustration demonstrates the plastic melt flowing between two fixed metal surfaces. The molecules that contact the metal tend to line up, with a large portion remaining in that direction after solidifying. The molecules that flow in the center of the part are disoriented and remain that way after the melt solidifies. The number of molecules that remain oriented depends upon how the polymer is cooled and its molecular weight. The larger the molecules or chains, the higher the molecular weight. The larger the molecules, the more difficult they are to orient, and as a consequence, the more they will restrict the melt flow. Shear stress, viscosity, and shear rate. The opposition to flow is better known as viscosity. Before further defining viscosity, we should define other terms, such as shear stress. Shear stress can be defined as shear force per unit area. Imagine two opposite forces with the same magnitude, F, pulling on a cube with surface area A. This shear effect can be defined as shear stress, theta. Now imagine that the cube is a small mass of thermoplastic melt exposed to two opposite forces of magnitude F. It was mentioned in previous courses that thermoplastic melt resists flowing and that it will stick onto the first static surface it encounters. This is the behavior that causes shear stress in the melt. In order to simplify our explanation, we will only consider half of the flow. The melt against the metal plate will still experience a force that will oppose the melt's movement. This force is the result of the disoriented molecules opposing orientation. Now we'll put coordinates. X is in the direction of flow, and Y is perpendicular to the flow. The molecules near the plate move at a different velocity than those at the center of flow. The profile of velocity v sub x, in the direction of x, illustrates a maximum velocity when y equals d, center of flow. If these molecules could be seen moving microscopically, we could see a gradual change in velocity between both extremes. This gradient of velocity in the vertical direction can be defined as shear rate. This change of velocity v sub x in the direction of y can be defined by shear rate equals change in velocity, delta v sub x, divided by distance, delta y. To describe shear rate, we imagine cars in the highway, one at a normal speed, 60 kilometers per hour, being passed by others going an exaggerated speed, 120 kilometers per hour. Two scenarios. A car passes with a separation of one lane and a second car with a separation of two lanes. In both cases, the change in velocity, delta v sub x, is the same, 60 kilometers per hour. Now when we consider the distance, delta y, the wind gust effect of the car passing with only one lane in between will be more significant. Let's see how shear stress and shear rate are related. Shear stress is proportionally equal to shear rate. This relation can be defined as viscosity, where shear stress equals viscosity times shear rate. Viscosity can be seen as opposition to flow. Let me explain. If viscosity increases, then the opposition to flow, or shear stress, will also increase. Definition: a Newtonian flow is that in which the viscosity is constant and independent of shear rate. The opposite would be a non-Newtonian flow, in which the viscosity is a function of the shear rate. Unfortunately, the flow of plastic melt is non-Newtonian. Because of this, the viscosity changes with the shear rate. In a simplified form, the viscosity changes with the injection speed. It has been experimentally demonstrated that viscosity decreases when flow or injection speed increases. This behavior is called pseudoplastic, distinct from Newtonian flow, in which viscosity is not affected by shear rate.
Why does viscosity decrease when injection speed increases?
This effect is called shear thinning, increasing fluidity by friction. During the injection process, the melt closest to the walls will harden as a result of heat exchange between the melt and the metal. The melt in contact with the hardened layer will experience a resistance to flow, resulting in an increase in friction. This friction is shown in the form of heat that helps maintain the temperature of the melt. So if the velocity increases, heat also increases, and consequently, viscosity or resistance to flow will decrease. Machine rheology. The plastic industry uses machine rheology in order to obtain the ideal injection time. It also uses the previously defined equations with some assumptions. Shear stress is equal to viscosity times shear rate. Intensification ratio equals melt pressure divided by hydraulic pressure. The second equation was described in previous modules and establishes the relation between the pressure that the melt sees in the injection unit and the hydraulic pressure of the injection unit. These are related by a constant called intensification ratio, R sub I. Melt pressure, P sub m, is a result of the forces or stresses that oppose the injection. From this premise, we can say that melt pressure is relatively equal to the sum of all the stresses that oppose the flow of the melt entering the mold. This is why the plastic industry assumes melt pressure is equal to relative shear stress. Combining that equation with the equation for intensification ratio, we obtain relative shear stress is equal to hydraulic pressure times intensification ratio. Another assumed effect is simplifying the determination of the shear rate by assuming that the relative shear rate is the reciprocal of the reading of fill time, T. Though relative shear rate and shear rate are not equal, even when they both have the same units, 1 per second, there exists a relation of velocity and time between them. What's most important is that this simplifies machine rheology and has been successfully used by many molders.
Why aren't they equal?
This industry simplification is based on cancellation of units. Let me explain. Remember, shear rate is equal to change in velocity divided by distance. If we substitute units in the shear rate equation, for example meters and seconds, and cancel units, we obtain shear rate equals 1 divided by second. Until now we are correct. It would be incorrect to say that, according to this result, the equation can be reduced to 1 divided by time. The component of the distance of the numerator is in direction x, and the component of the distance of the denominator is in direction y, and can't be canceled. Because of this, we recommend that you do not use the values of relative shear rate for any other formula that is not related to injection machine rheology. If we substitute the equations of relative shear stress and relative shear rate into the equation for viscosity, we obtain relative viscosity is equal to hydraulic pressure multiplied by intensification ratio multiplied by injection time. According to this equation, relative viscosity is simply determined by reading the hydraulic pressure and the injection time and later multiplying both of them by the intensification ratio. Remember that if the injection unit reads plastic pressure instead of oil pressure, the equation will be relative viscosity is equal to plastic pressure times injection time. Notes: these equations should only be used in injection machine rheology. Do not use these values for any other calculations or other scientific work. If the injection unit provides melt pressure, the shear stress is equal to the reading of the plastic melt pressure, or intensification ratio equals 1.0.
Why is it that the plastic industry uses definitions that don't exactly represent shear rate behavior?
Excellent question. Without diminishing the work of many molders who have used these equations for more than 20 years, and though it doesn't represent the defined behavior, it has standardized the determination of injection time.
How do we determine the ideal injection time with these equations?
We create a graph of viscosity versus shear rate and select a shear rate in which the corresponding viscosity is relatively constant. Remember to select a shear rate in which the viscosity is relatively constant. The idea is to select an injection time at which the melt is less viscous and relatively constant. The lower the viscosity, the easier the plastic flow, and consequently, the more efficient the fill. The idea is to maintain a constant viscosity cycle after cycle, filling the cavities with equal stress distribution and, as a result, obtaining a repeatable fill of the molded parts.
Where do I obtain the values for the equation?
The pressure is read at the moment of transfer, changing from injection to pack, and the time equals the duration of the injection stage.
Why do we use the pressure at the moment of transfer? Wouldn't the average pressure during injection be more representative?
We use transfer pressure for convenience. The average pressure would be more representative, but very few machines provide this reading. Those who don't feel comfortable using the previously explained equations can use rheology by power. Rheology by power. Another alternative is machine rheology by means of power, in which we graph injection time and the injection's peak power. Definitions. Peak power. The maximum power reached by the injection unit, normally at the time of transfer, changeover from injection to pack. This is obtained by multiplying the average injection flow by the pressure at the time of transfer. Peak power equals average injection flow times pressure at the time of transfer. Average injection flow. This flow is a function of the volume injected during the injection stage and the injection time. Average injection flow equals injection volume divided by injection time. Injection volume. This represents the injected volume from the plasticizing position to the transfer position. Injection time. This is the time that it takes to inject from the plasticizing position to the transfer position. The injection time decreases with an increase in injection speed. The purpose of these equations is to develop a graph of injection time versus peak power. The graph demonstrates the effect of injection time by power, in which the area below the curve represents the percentage of energy consumed for each decrement in injection time. The graph shows that power increases when the injection time decreases, or when the injection speed increases. Also, it shows that the energy consumed by the injection unit is more significant at lower injection times. For example, with a slow injection, reducing the injection time 0.5 seconds required 3,740 bars times cubic centimeters per second of power. With a rapid injection, reducing the injection time 0.17 seconds required 17,369 bars times cubic centimeters per second of power, 4.6 times more power for an insignificant reduction in injection time. The idea is to minimize injection time fluctuation by selecting a point on the graph where its variation is insignificant. Note in this zone that the injection time is relatively constant.
How do we create these graphs?
Though this will be explained in the next lesson, the traditional form is created using various injection speeds. Readings are taken of injection time and pressure at the transfer point for each injection velocity. These readings are then used to calculate their corresponding coordinates.
What range of injection speeds would I use to perform this rheology?
That question is a little premature. During the development of universal molding, it was established that the determination of injection process parameters must have standardized procedures and corroborated equations. In the next module, we will discuss in detail the recommended procedures.
Developing these graphs consumes resources and time. Is there a more efficient method of developing them?
Yes, there is. We call this method approximated rheology. Students at the University of Puerto Rico, Mayagüez, under the supervision of Dr. Ivan Bajes, helped develop this simple technique, approximated rheology. The development of an injection machine rheology laboratory consumes both time and resources. With approximated rheology, a mathematical prediction technique, the laboratory will take less than 1/3 of the time. Let's see how. If you work with rheology by power, you will note that there is a relatively lineal relationship between flow and power. If you work with conventional rheology, you know that there exists a lineal relationship between relative viscosity and injection time. Both graphs reveal that the intermediate points are approximated with the simple function of the line equation, y equals y sub naught plus m times x. Let me explain. Knowing slope m and intercept y sub naught in the y-axis, we can predict intermediate points. Let's see an example. In the optimization of a process that injects a volume of 29.17 cubic centimeters, we obtained readings of injection time and transfer pressure at 2 injection velocities. In this case, the injection velocities are 193 millimeters per second and 19 millimeters per second. Using the previously described equations, average injection flow equals injection volume divided by injection time, peak power equals average injection flow times pressure at the time of transfer, shear rate equals 1 divided by injection time, relative viscosity equals plastic pressure times injection time. We can calculate and include the values listed in the following table. For rheology by power, we can calculate flow and power, and for traditional rheology, shear rate and viscosity. We can now use the coordinates to determine the lineal equations for both cases. Let's first look at the lineal equation of rheology by power. The equation will be flow equals 0.0016 times power plus 4.5968, or power equals flow minus 4.5968, all divided by 0.0016. Let's now look at the lineal equation created by conventional rheology. The equation will be viscosity equals 498.8 times injection time plus 31.322. Next, we determine 8 equidistant injection times between the existing times. See the injection time column. Then we complete the calculations for the average injection flow and shear rate for each corresponding injection time. Finally, we determine the corresponding approximations for viscosity and power using the previously determined approximations. Power equals flow minus 4.5968 divided by 0.0016. Viscosity equals 498.8 times injection time plus 31.322. Now print the corresponding graph. Approximated graph utilizing machine rheology by power. Approximated graph utilizing traditional machine rheology. Now let's look at 2 superimposed graphs. Approximated rheology with 2 points and traditional rheology with 10 points. The graphs of injection time versus power clearly corroborate the validity of approximated rheology.
Which is more recommended, traditional rheology or rheology by power?
Some of us prefer rheology by power since the definitions describe the effect with more conviction. Now you can use the method that makes you feel more comfortable, since both rheologies give good similar results.
In a process optimization laboratory, which of the two should I use, conventional or approximated rheology?
Approximated rheology is preferred, since both processes function conceptually the same. The principal reasons are that approximated rheology consumes less time, material, and resources.
Selecting injection time in the plateau zone of the graphs is subjective and varies with the Moldis criteria. Is there some technique or equation that standardizes the determination of injection time?
Yes, both the equations and the procedures exist. Universal molding established that, during the determination of molding parameters, the result should be relatively equal, independent of who the molder is. Equation to predict injection time. During the development of MU, It was decided that all parameters should be determined by means of clear procedures and equations. This was done in order to guarantee similar results between molders. This situation was resolved with the collaboration of multiple molders who had a clear understanding of machine rheology. Using rheology graphs with their coordinates normalized in percentage, the universal molder selection tendencies were averaged. With various graphs like the one below, the question was formed: where does the plateau begin in these graphs? The average was evaluated and the following formula was obtained. T plateau equals T minimum plus T maximum minus T minimum divided by 9, where T minimum equals the injection time corresponding to the maximum injection speed. T max equals the injection time corresponding to the minimum injection speed. And T plateau equals the injection time at the beginning of the graph's plateau. With this equation, we calculate the injection time, where the rheology curve starts the viscosity plateau or starts a relatively constant injection time. Based on this simple calculation, we determined that the ideal injection time should be less than that obtained by the equation. T ideal is less than T minimum plus T maximum minus T minimum divided by 9.
Where in the plateau is the ideal injection time?
This will depend upon the type of industry. Conventional molding industries can select an ideal injection time in the center of the plateau. Industries that mold materials that are sensitive to injection speed, such as rigid PVC connectors, should choose a time that is close to T plateau. Industries with a high injection volume, such as closure molders, should choose a time close to T minimum. This subject will be discussed in more detail in the next module, determining injection speed. Notes: don't try to rush the determination of injection time. These procedures will be presented in the next modules. Remember that this is costly equipment, and trying to work with it without completing all modules could cause breakage or an accident.
Let's review. You have completed this lesson.